Back students, in this video we are going to talk about the potential energy of a dipole in an external field. We'll start with that and then we'll continue to do the example problem, and also we'll discuss about the properties of conductors. First, we'll talk about the potential energy of a dipole in an external electric field. So, potential energy of a dipole in an external electric field. Let me assume a constant electric field. Okay? So that's the external field, a uniform electric field. Okay, so it's going to be like this. The field is going to be like this, in this direction. So this is E. So this direction. Let us suppose I have a dipole in this field. Let's say the dipole is at an angle theta. Okay. This is my dipole. So I may have a plus Q here, and then I will have minus Q here. And you also know that this is 2A, right? This is 2A distance. So now what is going to happen? So this plus charge will experience a force. E is in this direction, so it will experience a force in this direction. Okay, there will be a force in this direction. The negative charge will be attracted, in this direction. So again. So what is going to happen? So if I have a dipole like this, one end is getting attracted, is repelled this way, and the other end is going to be pulled this way. So it will start doing this, and they are connected, right? Because there is a molecular bond between the atom, between these two atoms. Okay, so these are charges. That is what we call as the dipole. For example, if you take water, which is a natural dipole, so you have H and OH minus parts of water, so they are connected. They are connected to the molecular force of attraction. So they are together, H and OH minus. That's a dipole. So H is going to be repelled and then OH is going to be attracted. So we will start rotating. You can see that. It's like this, and it starts rotating. And then once it crosses here, at this point, the force on them will be equal, because equal amount of charge, and the field is constant. That is the assumption we have. So this will be repelled this way, this will be attracted this way, and then the net force on that will be 0, which is true in any case. But then when the forces are separated, then you are going to experience a torque. But then when they are when the forces are acting on the same line, you won't experience a torque. But then when the body has moved from this position to this position, it will gain some velocity, and it won't stop. So it will continue. So as it continues here, you see this is going to be repelled in this direction, and this is going to be attracted in this direction, right? So this is positive, it's negative. So repelled, attracted, negative, it has come here, and it's going to be repelled in this direction, attracted in this direction. You see it's going to slow down. From here to here, it will pick up speed. And then from here to here, the speed will be reduced from here to this position. It will be reduced, right? So then what happens? So it starts from here and then it comes back, then it stops. As it stops, then it will start moving in this direction because it's still going to be repelled in this direction. It's positive. Repelled in this direction, we attract this direction, so it will start doing. Then here it won't stop because it will gain some speed and will continue and will slow down, and then here it will stop, and again it will be pushed in this direction, so it will start oscillating like this. So the point here is that it is going to experience a torque, and in the first lesson we also found the torque. What was the torque experienced by this? The torque experienced by this was given by the expression P cross E, where P is the dipole moment of this dipole, which is 2aq, with a vector going from negative to positive. So this was your P, right? This was your P, and this was E. So P and E would have an angle, and the torque experienced by that was P cross E, which was equal to PE sine theta, right? Okay. Then what happens now? We are going to find the potential energy of a dipole in an external electric field. So what did we say for potential energy? Potential energy is the work done by an external force against a conservative field. Here, which is the field? E is the field. And what is E going to do? It's going to move the charges like this. Then what should your external force do? It should try to work against that force. Okay? So let us suppose that let me take this as the angle, say theta naught. At this position, it is theta naught. Okay? Now, what is it going to do? E is going to push it in this direction. But what should you do? You should do work against the force. So I am going to move it in this direction to another angle, maybe, let's say, here. Okay, so plus minus. This angle I am going to call as theta 1. So this is my original angle, and I am going to move it from here to this position, theta 1, and I will be doing work against the conservative field. Clear, right? Because the conservative field will be trying to push this dipole from this position down, but then I am doing work against it this way without acceleration. Understand? Okay. So the work done by the external force must be equal to the negative of the work done by the electric force. You know. So as it is moving from this position to this position, E will also do work, but that's negative work. You see, the motion is in this direction, but then E is acting, the force is acting in this direction for E, then motion is happening this way, so you will do negative work. And then you will do, or the external force will do, negative of that negative work, so it will become positive. Okay? When torque is involved, the work done is given by this expression. Okay, work done when torque is involved. 2 is the torque, then work done is given by the expression integral to d theta. This is the work done. This you may have come across in your 11th standard, and if you don't understand that, let me try to explain, like how does it relate to the general definition of work done. What is the general definition? So normal definition is what? It is work done is equal to force into displacement. Okay, force multiplied by the force in the direction of displacement multiplied by displacement. That's work done, right? Okay. But then suddenly, like I'm bringing angle d theta and then tau. Then I'm going to explain how this is true. This is something that you're supposed to know from your 11th standard, but I'm going to explain it anyway. Okay. Let us suppose that a body, okay, this is the origin, there is this body here, okay, it is going to experience a force in this direction. Okay. So R is the radius from here, like from the origin, like this is the R. So what is the torque experienced by it? The torque experienced by is equal to R cross F. Okay. So that's the torque. But what's the work done? Work done must be in the direction of the force, right? Or the motion. The motion in the direction of the force, or force in the direction of motion. So it's right. So this must be, suppose there is a displacement like this. Let's say there is a displacement d r that takes place there. Okay. So that there is a displacement in this direction, in the direction of force. But how can I write that? Let's say it is going to be d theta. So dr can be written as r into d theta. Okay. Then what's the work done? So work done is equal to force into dr. So the small work done. Okay. The force into dr there. So what is F? Okay, F I will keep it like that. And then what is dr? Dr is r into d theta. It's from S is equal to r theta formula, right? So when you have a small curve, then you will have S is equal to r into d theta. So that would be F into r into d theta. But what is F into r? F into r is actually the torque tau. So tau d theta is the work done. So I get that here. The small work done is tau into d theta. So this is the reason why you have this expression. What it actually means is F into dr only. Okay. So you have, so for small work this is F dot dr, and then if you keep adding the small pieces of work, then you will have an integral here, the summation of those things, that is tau d theta. That's what we will have here. Okay. So this is the reason you have here. So let's come back to this. So now, what is the work done by the electric field? The work done by the electric field is equal to the sum of all those small works that you've done. Okay. So that would be integral. What is tau? Okay. Tau d theta. Tau as a function of theta. Okay. So tau as a function of theta, and then d theta. So this is and you're going from theta naught to, so theta 1, right? So theta naught to theta 1. So this is what you have to do. Okay. Let's see what you're going to get here. So that is going to be theta naught to theta 1. Now what is it? Theta? It is P sine theta. That is your torque. That's your torque. And then d theta. But as you go from theta naught to theta 1, you see d theta is a positive value, and then P sine theta will be a positive value. Okay, you will get some number here. Okay, so this is actually positive. But what are you supposed to get? You're supposed to get negative, right? So d theta is going to be positive because theta is increasing here. So the final theta will be greater than the initial theta. So d theta will increase, will be a positive number. This is a positive number. So positive into positive will give you a positive value. So you need to assign a negative sign to that because the work done by W is going to be negative. Why? Because the torque is in this direction or the force is acting in this direction, and then you are moving in the opposite direction. So you need to have minus P sin theta d theta there. Okay. But what done by U or the external force? So that must be W external is equal to minus of WE. So that gives you minus of minus theta naught, theta 1 and P sin theta d theta. So that makes it plus theta naught to theta 1 P sin theta d theta. So that is the work done by the external force. And I need to integrate this. So what would I get if I integrate? If I integrate this, this is going to give me sin theta. P is a constant. Okay, P is a number, E is a number, constant numbers, and then theta can change from theta naught to theta 1. So sin theta d theta, integrate, and it will give you answer minus cos theta. Okay, the whole thing will have to be written theta naught to theta 1. Okay, and when you do that, the external is going to be so minus P cos theta 1, right? Minus P cos theta 1. The top limit first, cos theta 1, then minus of minus P cos theta naught. Okay, so that is going to give you W external. It's going to give you P cos theta minus P cos theta 1 theta naught. Okay. So this is the work you are going to do for moving this dipole in this field from theta naught to theta 1. So this is the work you will do. Okay. Suppose this is 10 units or something. Okay. There are two different values you can get actually. You see, if you think about it, so this can be 90 units and this can be 100 units. So 100 minus 90 can give you 10. Okay, that can be, one can be 110 and then the other thing can be 100 and then the difference would still be 10 units. So you can see, as I have discussed already, that when you talk about potential energy, the difference in potential energy is important, not the ultimate the value of potential energy. For example, if I am standing on the ground floor here, okay, so I can assign potential, this potential is 0 to the floor here, and then this is, what is the potential of this? This mgh. Okay, this will have some value. Okay, that is given by mass of this and gravity 9.8 meter sine squared multiplied by the height from there, mgh. So if I drop it, then what will happen is it will start fall from here to that position, right? So the potential difference is important here. Okay, you keep this in mind. And then let's do the same thing on the first floor or the second floor. Again, I can assign 0 to that floor. And then again, mgh, as I drop here, then it will have the same kinetic energy as it reaches that floor. Okay? So the potential energy difference between that point and this point, that's important. And that is going to give you the amount of kinetic energy you are going to get there. See, even in that case, I can take this as 0, the ground as 0, and then assign, say, maybe 13 feet as one point, and then 13 feet plus h distance as the other point. Even then, the potential energy difference will be the same, right? So the choice, the value that you assign here is not going to change the potential difference. If I put, say, 100 here, it could be 90, okay? Or if I put 100 here, it could be 110. And if I put, say, 110 here, that could be 120. So the difference could still be 10. And if I put 1000 here, then that would be 1010. So when it comes to potential energy, the potential energy difference is important, not the absolute value that you assign. It doesn't really, the absolute value doesn't make any sense. But once some value is given here, then this value will depend on this value. Okay, like this. Once I assign 0 as the potential energy for this flow, then this will have mgh. That's the thing. Okay, and once I assign 0 as the potential energy for the first floor, then the point from there, the mgh, the other point will have the mgh value. Or if I say this is 0, then the first floor will have one value based on this, and then that mgh will have a different value there. But you see, but the difference between that point and then that floor would be the same as this point and this floor. And if I drop things, both will have the same kinetic energy. As this reaches this floor and that reaches that floor, the pen will have the same kinetic energy, right? But just because you have given a different number to that floor, it is not going to change the kinetic energy. So when you talk about potential energy, the potential energy difference is important. Okay, so here the potential energy difference is this, P cos theta minus P cos theta 1. Okay. So if that is the case, I can choose some point as a 0 potential point. You see, if you remember, when we talked about a single charge, okay, or a system of charges, and then when we try to find the potential due to that system of charges at a particular point, we said that at infinity the potential energy will be 0, and then you brought a unit positive charge from infinity to this position, or you took any charge, you brought from infinity to this position, and at that position it will have some potential energy value, right? So the reference point was infinity. You took that as 0. So likewise, what are you going to take here as 0? The point that you take as 0 is obviously it's 90 degrees. Why? Because you notice here, cos 90, the initial point, if theta naught is equal to 0, the initial point, theta naught, the angle is 90 degrees, then this term will become 0, right? The potential energy is 0. Then cos theta 1, the other, any other angle will have some value, right? So here, your theta naught, if you choose theta naught as pi by 2, then the potential at theta naught will be 0. And any other point would have some value. Okay, so that would become the potential of that point. Okay, so I can say that if we choose theta naught equal to pi by 2, then work done by the external force can be given by PE cos pi by 2 minus PE cos the any theta. Okay? So what is the potential at theta 1? It's simply minus PE cos theta 1. What is the potential at say theta 2? Simply minus PE cos theta 2. So now, if I choose this as my zero potential energy, then every other angle will have a potential energy. Again, what is important? The potential energy difference. It is only a question of choosing one point as a reference point, or one angle here as the reference angle. So here 92 is a 90, or the theta is equal to 90 or pi by 2, then that is the reference angle. So that is your ground state. Okay, and any other angle will have some value. If this is ground state, my floor is the 0, then this is mgh. You see, the potential energy at this point is mgh. So this is an attempt like that. So I say this 90 degree is when the dipole will have no potential energy. Okay, that's my 0 point. And here I have an angle, say theta 1 from the x-axis, then I will have some potential energy value. And what would that potential energy value be? Simply minus P cos theta. So I will say that work done is equal to minus P cos theta. Okay? Well, you see, it has the hallmarks of a dot product, right? P E cos theta. P is a vector, E is a vector, and there is an angle between them, and you are getting cos theta there. So I can write this as a dot product of two vectors, the E vector and then the P vector. So I can write this as the potential energy of the work done by external force is equal to minus P vector dot E vector. So this is the expression for potential energy of a dipole in an external electric field. So for any angle I can find the potential energy. I can assign any potential energy. For example, 30 degrees is going to be P minus P cos 30. That's the potential energy at that point. 60 degrees minus P cos 60. That is the potential energy at that point or that angle. 45 degrees minus P cos 45. That's the angle. That's the potential energy at that angle. Okay. So for any single angle, I can have a potential energy value. And when I move from one angle to the other angle, I will take the final angle, potential energy, and subtract from it the initial angle potential energy, then I have the potential energy difference. It is so simple. Okay. So the reference angle is pi by 2. Okay. At pi by 2, what is the potential energy? 0. And any other angle, you will have potential energy. And when you go from one angle to the other angle, what is the potential energy difference? P final minus P initial. Simple. Hope it's clear to you. Remember this. This is work done. Potential energy of a dipole is simply minus P dot E. Okay. P vector dot E vector. Okay. That itself is like a mnemonic, right? P and E. Potential energy minus potential energy. Hope that's clear to you. Okay, now let's do an example problem, example 2.6. A molecule of substance has a permanent electric dipole moment of magnitude 10 power minus 29 coulomb meter. A mole of the substance is polarized at low temperature by applying a strong electrostatic field of magnitude 10 power 6 volt per meter. The direction of the field is suddenly changed by an angle of 60 degrees. Estimate the heat released by the substance in aligning its dipoles along the new direction of the field. For simplicity, assume 100% polarization of the sample. So, what is happening here? We are talking about a substance which has a dipole moment of magnitude 10 power minus 29 coulomb meter per molecule. So, for example, if we take water molecule, okay, let's suppose that this is water molecule. So, you have H plus and then OH minus. So, you have a dipole there. So, per molecule, it has this value of 10 power minus 29 coulomb meter. They are not saying that it is water, but I am just giving you an example. You know that water is a permanent dipole, so it has a this is a molecule like water, so it has a dipole moment of magnitude 10 power minus 29 coulomb meter per molecule. Okay. So a mole of the substance is polarized. So you take a mole of the substance and then you are polarizing it. What do you mean by polarizing? You are going to keep it in an external electric field. So if you take individual molecules, they may be, they may have this dipole moment in different directions. Okay, one molecule may have a p this way, another molecule may have a p that way, and then the third one may have dipole moment this way. So they may be randomly oriented. Even though they have a dipole moment, each molecule may have a dipole moment, they may be randomly oriented. But then when you keep all these molecules in an external electric field, then they will all align. Okay? So that is what you call as polarizing a substance. So you take a substance and then you subject it to an external electric field, then each molecule of the substance gets polarized. So this process is what you call as polarization. Okay, and the electrostatic field strength is given by 10 power 6 volt per meter. So volt per meter is the same as the unit you have for electric field intensity. So for electric field intensity, what did you have? You had Newton per coulomb, right? So volt per meter will also have the, effectively will work out to be the same Newton per coulomb. I'll do it here. So volt per meter, E, what is E? E is actually force per charge, so that is Newton per coulomb. So here another unit for that is volt per meter. How? That is easy, right? If I multiply this by m, and then if I divide that by m, then what do we get here? So this is N into m, that is joule per coulomb per meter. Joule per coulomb is volt, so you get volt per meter. Okay. So volt per meter and then Newton per coulomb, they are the same. So another unit for E is volt per meter. You knew that it was Newton per coulomb, so it is also volt per meter. So that's 10 power 6 volt per meter. So now you are polarized. Okay, so now they are oriented in a certain way. They are all oriented in a certain way. Now you are changing the direction of E. So what happens now? By an angle 60 degrees, you are changing it by an angle 60 degrees. Then they are already polarized in this way. Okay, now E is in this direction. Now they try to polarize in this direction, right? Now they start moving in this direction. So it is like it is like dropping a stone. Okay, the stone is at this height. Suddenly, it's dropping. Okay. Likewise, initially they were polarized at one angle. Now we change the angle of E. Then they'll start following E, right? So when they start following E, then they'll start moving. So that that is what they mean here. So that is how fast will they move, and what is the amount of energy that is going to get converted into kinetic energy, okay, and effectively it's as heat, okay. From the 11th standard that temperature is a measure of the kinetic energy, right, of the molecule. So you have potential energy and they get converted into kinetic energy, then that is also, you will get heat out of that, okay, at the molecular level. So that is what they are talking about here, okay. So for simplicity, assume 100% polarization of the sample. I hope you understand the problem. You have a dipole. Now you subject it to an electric field. In fact, like you have substance, a permanent dipole substance. Okay. So, but individual dipoles are randomly aligned. So now you subject that material to an external field. Now all the molecules will be aligned with the electric field, like this. They are subjecting it to an electric field. So now we are polarizing them in this E direction. Now they are polarized. Now what you do? You change direction of E, like 60 degrees, like that. Then what will they do? They will try to come back. As they come back, it is like falling, right? It is like falling. So the potential energy gets converted to kinetic energy. So that kinetic energy will come out as heat. Okay? So they want you to find the amount of that energy. Okay? So how do you do that first? So example 2.6. Example 2.6. You have, so what is given here? P, I'll write it as a small p because it's for molecule, right? So that is equal to 10 power minus 29 coulomb meter. Okay? And what is happening here? You are subjecting this substance to polarization. You are keeping the substance in an external electric field, E. So what happens is, suppose that field is in this direction. So E is in this direction. Let's suppose E is in this direction. So what will happen now? All these molecules which were randomly, whose dipole moments are randomly oriented. So one P was like that, another P was like this, okay, and then third was like this, and then fourth was like this, and maybe fifth was like that, and sixth was like this, seventh was like this. So all these individual molecules, they had their dipole moments initially, they were not aligned. But now you are subjecting them to an external electric field. And what will happen? They will all align to the electric field. So effectively you get P here, and then P here, and P here, and P here, P here. It's like that. So they are aligned like this. Okay? So as they align, what is a net P you will have? Previously, even though each molecule had a P, because they were randomly aligned, you will not get any net because they get cancelled. Okay, they're randomly oriented. If something was in this direction, you can find another thing in the opposite direction, so they could cancel each other out. Okay, but now you are aligning them to the external field. Okay, so all of them will contribute. They are all aligned in the same way. So the net P will now not be 0, but this P, which you call as a capital P, is equal to the number of molecules multiplied by the individual dipole moment. So that is equal to n into the small p. But what is n here? N is actually 6.022 into 10 power 23. Right? You have taken 1 mole of substance, so you can you're going to have 6.022 into 10 power 23 molecules in that substance, multiplied by 10 power minus 29 coulomb meter, and that would effectively give you a net P for the entire substance of 6.022 into 10 power minus 6 coulomb meter. So that's your P. Okay. So E value is given. What is E value? Is given as 10 power 6 volt per meter. Okay. So that is E value. So what are they doing now? Now it's all aligned in the field of in the direction of E. Now you are changing the direction of E like this, 60 degrees. Now the direction of E is changed like that. Okay. So you see, you are going to have an angle of 60 degrees between the P's and then the E. So it is like, now this is like the ground, right? So it's like, now what will they do? They try to fall from here to there. Try to fall from here to this position. Is that clear? Okay. So, so it is like something falling from a height to the ground. So how do you find the potential energy when it is at a height? So that would be initial 0, and this would be that potential and this potential. This is the final, that's initial. So when we move this body from the initial 0 to this position, then that is how you can you calculate the potential energy, right? Okay. So this is the flow. So this is the position now. So what's the potential energy? The potential energy will be the work you need to do to move this from the floor to this position. Yeah. Only then they will drop back. Correct? Drop back to the position. So the work done in moving something from here, this angle, to this angle. Okay. That's the potential energy. Okay. So now they stop moving back, right? So they become kinetic energy now. So to calculate the potential energy, how do you do? So by initial 0 theta I initial. What is theta I? So what is potential energy first of all? The potential energy is equal to potential energy at theta final minus potential energy at theta initial, right? But what is theta initial in this case? Theta initial is this, that E, because that's a flow, right? So that is 0 and then this is 60. I can treat this to be 0 and this to be 60. Okay. So what is going to happen here? This is U of 60 and this is U of 0. But what is U of 0? So U of 0, we know that's equal to minus P cos 0. Okay. So that is equal to minus P is what? Minus P is 6.022 into 10 power minus 6. Yeah? 10 power minus 6, this is P. Okay. Multiplied by E is 10 power 6. 10 power 6 volt per meter, and this is going to give me minus 6.022 joules. So that is the initial kinetic energy, potential energy. There is a flow at the flow. And now I am moving into this position which is 60 degrees, right? So that is U of 60 is equal to minus E cos 60 is equal to minus 6.022 into 10 power minus 6 into 10 power 6. Actually cos 0 is 1 there, but now cos 60 is, okay, cos 60 is actually 1 by 2. So I'm going to get minus 3.011 joules. Okay. So that is my final. So what is the net? What is the potential energy? That is final minus initial. So U60 minus U0, that is equal to minus 3.011 minus of minus 6.022. Okay, so it is roughly equal to, I mean, if I take this to be 022, it is roughly equal to 3 joules, right? This plus 6 minus 3 roughly equal to 3 joules. So that is the amount of work I need to do. So now when they go back, then they will release this amount of energy. Okay. Because like as I said, this is the flow, this is the height, so it will come back, go back there. So then that's what it will do. Okay. So it will become kinetic energy now. I hope the idea is clear to you. So first you have aligned. Okay, E was like this, but now you are changing E to this. So what does it mean? It is like you are creating a pit. Okay? It is right now, it is like this. Now we are creating a pit. Now it will start falling into the pit, right? But then how do you calculate that MTH? Well, you need to consider the pit as the bottom of the pit as the initial position, and then the top of the pit as the final position. So that is why this you are considering as initial, this is final, so you need to take it from the pit to this height. So you go from 0 to 60, and now it will start, that potential energy will become kinetic energy. Yes, so this is how you calculate it. Hope this is clear to you. Okay. So we also said that every angle, the moment you have an angle, then you can find the PE, right? So if this is 0, then minus PE cos theta would be this number, and if this is 60, then minus PE cos 60 would be this number. And we said these numbers are not important. When it comes to potential energy, the difference between those two numbers is important. So 3 joules of energy is there. Now as it goes back, and that those 3 joules will become heat energy, kinetic, and then become heat energy. So this is clear to you. Okay, the next topic that we are going to cover is the electrostatics of conductors. You have a conductor, you either subject it to an external field or you bring a charge near it so that the charges are induced in the conductor. Suppose I bring positive charge near it. Suppose it's a conductor and I bring positive charge near it. Then this positive charge will create a field around it. So the free electrons in this conductor will start moving towards this positive charge, right? So they will gather here on this side, leaving the other side positive. Okay. So in the static condition, they will all be set, right? So initially they will start moving because we are bringing the charge. They will start getting aligned. So this static condition, the negative charges will gather here, and then the positive charges will be on the other side of the conductor. Okay. If that is the case, then what do you think is going to happen to the conductor? What are the things that you can infer from this position, from this condition? Okay. One thing is the first thing is this. The first thing is that the electric field in the static condition, electric field inside the conductor is 0. So for example, if you have a conductor, this is a conductor, this is the thickness of the conductor, let's say. E inside the conductor must be 0. It doesn't matter whether you have whether you have charged it or you are subjecting it to an electric field. Suppose there could be an electric field here. I can create an electric field here. Okay, this could be I can keep it in an electric field. Okay, okay, it's not right. Let's come back to that. Okay, so it could be like this. There could be an electric field like this, like this, like this position. Okay. But inside the electric field is actually 0. So why? The reason is this. The conductor can have many free electrons. If the field inside the conductor is not 0, then they will start moving, right? Because if you have free electrons here, if there is an E inside, then they will start moving in the direction opposed to the direction of the conductor. So you will have a current because the charges will be moving. So you will have a current. But at the static condition, there is no current. There is no current flowing in it. So the charges may go and accumulate in these places. Like negative charges can come here and positive charges can be here. But the charges will accumulate and no further movement of charges will happen. And that is why you call it as a static condition. So since the current inside the conductor is 0, you can only conclude that there is no E inside. So whether you have a neutral conductor or you are keeping it in an electric field, or you bring a charge near it, or whatever you do, one thing is certain, that is the field inside the conductor is 0. That's the first point. And the second point is this. The field on the surface, at the surface of the conductor, okay, you can have a field here, right? Inside it is 0, but the field on the surface must be normal to the surface. The field must be normal to the surface. See, I have drawn the picture here, right? Suppose let me take an irregular conductor like this, a conductor like that, okay, an irregular wire or something. You see, and this is the surface of the conductor, and the field here must be normal to the surface. For example, if this is the tangent here, then the field will be like this here, and then if this is here, tangent here, the field will be like this, then the field will be like that, okay, and then the field would be like this, and the field could be like this. See, this could be E1, this could be E2, this could be E3, could be E4. But you can see that the field will always be normal to the surface. For example, if you have a conductor like this, a regular conductor, okay, then the field can only be normal to the surface. Inside the conductor, E is 0, but on the surface, you can have E. But that E will be normal to the surface. E will always be normal to the surface. It can never have an angle to the surface of a conductor. Why? The reason is, if you have, suppose you have, this is a conductor, and then let's suppose that you have E like this. Then what happens? You can have a vertical component and also a horizontal component, right? Okay. And there are free electrons on the charges. Let's suppose the free electrons are there. Okay. What will happen now? If there are free electrons, then they will start moving in this direction. The free electrons on the surface will start moving on the surface. So you will have a surface current. But in a static condition, you cannot have current because everything is gone and then stays in its place. Okay, it's static. no free electron is moving there. Okay, so since charges are not moving on the surface, there is no surface current, because we are talking of static electrostatic condition, so this cannot be present. The horizontal component cannot exist, so only the vertical component can exist. So you can never have an E like this. E can only be perpendicular to the surface of a conductor. Okay. So that is the second point. The first point is E inside a conductor is 0, and then the second point is the field on the surface of the conductor must be perpendicular to the surface. If it is regular like this, then it will be perpendicular at every place. Okay? But if it is irregular conductor, like at one point it may be like that, another point may be like that, another point may be like that. But at every point, it's going to be normal to the surface. Okay. And the third point is that, suppose you are charging a conductor, so you are going to give excess charges. Okay? Maybe you are giving some electrons. Okay? Where are they going to be? Are they going to be inside the conductor, outside the conductor? Where are they going to sit? The excess charges that you give to a conductor, where will they go and reside? The answer is that the excess charges you give to a conductor will always reside on the outside of the conductor. They will always be on the surface. They cannot be inside. Suppose there is a charge inside. Some of the charges go and sit inside. You give, say, 10 charges. Say 3 sit on the outside, 3 sit on the outside here, and then like 4 go and sit inside the conductor. Can that happen? It cannot happen. Why it cannot happen? Because if there are charges here, you see, I can have a Gaussian surface around it, right? If you have a Gaussian surface around it, then there would be a net field here. If there is a net field, then there must be a net charge here, right? You know, from Gauss law, we know, right? The flux coming out must be equal to the charge inside divided by epsilon naught. But what did we say first? E must be 0. Why is E must be 0? If E is not 0, then there must be current. There are free electrons, they should be moving there. Okay? So if there are excess charges inside, then they will set up a field, then the free electrons will start moving. So you will have a current there. Okay? So the free electron, the excess charge that you give, cannot go and sit here. Okay? So the excess charge that we give will always reside on the surface of a conductor. So that is point number 3. And then what's the fourth point? The fourth point is that the electrostatic potential is constant throughout the volume of the conductor. It's understandable. You see, if I give charge, what is this? You will have a potential here, right? And suppose I have got a conductor here. I have given, I will do fourth. So there is a conductor. I have given charges to it. It is sitting outside. What do you know? E is 0 inside. And then there will be set up a field. Okay, like this. Okay, set up a field there, a negative charge. Okay. Now I can calculate the potential. Right? I am going to bring a test charge from infinity to this position. So I will have to do work up here. I will keep doing work up here. Okay. So as I bring the charge here, I need to do work up till here. But the moment I go inside, will I do any more work? No. But there is no E. Only up till here I will do work against the field. So inside, I will not do any further work. So whatever work I have done up till here is the work I have done. So any further movement inside will not require any work to be done. Why? Because there is no field inside. So what would I work against? So whatever work I have done up till here will hold good. No further addition can be made. Okay. So up till here whatever I find, or the potential I find, will remain here. So inside the conductor, the potential is constant, because the work that you have done up till here doesn't change once you go into the conductor. You don't have to do any further work than you have already done. So potential will remain constant inside the conductor. So these are the 4 points that you need to remember. The first point is the field inside a conductor is 0. Why? Simple. If there is a field, the free electrons in the conductor will be moving, so you can experience a current. But we are talking about electrostatic condition where there is no current. If there is no current, there cannot be any field inside the conductor. E has to be 0. That's the first point. Second point, the field can be on the surface of the conductor, because charge is and the field has to be perpendicular to the surface at every point on the surface. Why? If it has a horizontal component, then the free electrons on the surface will stop moving in that direction. Then there will be surface current. But the static condition, there is no current, which means then this component cannot exist. So E has to be perpendicular to the surface. That is point number 2. And what's the third point? The excess charge that you give a conductor can reside only on the outside, on the surface. They cannot go inside. Because the moment they go inside, then they will set up a field. Then if they set up a field, then the free electrons in the conductor will start moving, then you will have a current. So in electrostatic condition, there is no current. So the charge that you give cannot go inside and then sit. The charge will have to sit outside. Okay, that is number 3. And number 4, the potential is constant inside. So you will have a V. E can be 0, but you may have a non-zero V. But that will be constant throughout. Because the work you have done up till here is not going to change as you take the unit positive charge inside. Because you will not do any further work than this. But before this, you will do some work up till here, more work up till here, even more work, even more work, even more work, because you are resisting the field, right? But once inside, you are not resisting anything. So you don't have to do any further work here. So the potential inside the conductor is constant. So these 4 points we have to remember. Hope this discussion is clear to you. If not, let me know.